All right, guys, Mr. Antonucci here, and in this second video, we're going to talk about how to use slope fields to approximate solutions to differential equations. So, lots of times, differential equations can actually be difficult or even impossible to solve, but there is a graphical approach called, or referred to as slope fields that you can use to actually learn a lot about the solution, the differential equation, and that's our key word here, a slope field, or sometimes they're called direction field. It's a graphical representation of a differential equation, dy dx equals f of xy. And what this means is that your derivative might be in terms of two variables, x and y. And what they do is they put short line segments at selected points that indicate the slope of the solution curve at those points. So this helps provide a visual guide to generate the general shape and direction of all possible solutions to the differential equation. So if we want to sketch the slope field here for the differential equation y prime equals x minus y for these 3 points. So if I have y prime equals x minus y, I can make like a table of values here. Um, the first point is negative 1, 1, and y prime is the x value minus the y value, which is negative 2. So at the point negative 1, 1, I would draw a short little tick mark tangent line-ish looking thing that has approximately a slope 2. The next point, 0, comma 1, would be the x and y value. So y prime is equal to the x value minus the y value, which ends up being negative 1. So there we go. Now notice the slope of that tick mark is still negative, but it's not as steep as the previous one because the slope is negative 1 and not negative 2. The next point is 1, 1. If you substitute that into the differential equation, you get 0, and you would have a horizontal tick mark at that case, in that point. Now, it's not going to happen with this one, but sometimes if you substitute a point in and it makes the differential equation undefined. So, for example, if you had y prime equals y over x and you wanted to use the point like 0, 1, you would be dividing by 0 in that case. And there you would perhaps have a vertical tangent. Depend on some other factors there, but just wanted to bring that up. So in this case, example 4 here, we're going to match each slope field with its differential equation. And so what we want to do is try to look for patterns that are going to line up with the equation. So for example, if I look at equation 2 here, y prime is equal to x. That means as when x is positive, the slopes are going to be positive. When x is negative, the slopes are going to be negative. When x is 0, the slopes are going to be 0, and there's no points that are going to be undefined. Now, when x equals 0, that's going to be the vertical, like a vertical band at the line x equals 0, which is actually the y-axis. And when x is 0, the slope is 0, so you should have a bunch of horizontal tick marks. Well, graph A satisfies that. If you look at graph B, all the tick marks are not equal to 0. Now, at the origin, it is, but since equation 2 only depends on x, when x is 0 at any y value, x or 0 comma whatever the y value is, the slope should be 0 or a horizontal tangent there. And same thing with C, it doesn't satisfy that. So C and B are out, and equation 2 goes with A. Similar thing with equation 3, except we're doing this with respect to y. So if y is 0, okay, then the slope should be 0 for any point that has a coordinate where y is 0, particularly along the x-axis, because the equation y equals 0 is a horizontal line across the x-axis. But we want to remember that we're looking at all points that have a y coordinate of 0. So it's going to be whatever the x number is, comma 0. Graph B doesn't have horizontal tangents at each of the points on the x-axis, but graph C does. Another thing is that since equation 3 is only dependent on y, Y prime is going to be positive when y is positive, and the slope is going to be negative when y is negative. So that means that for any points that have a positive y coordinate, so everything in quadrants 1 and 2, the slope should be positive. And in fact, the slope should get increasingly steeper as you move up. And that's kind of what happens here. Similar as you move down below the x-axis, the y values get increasingly negative. The slopes should all be negative and they should get steeper in the negative direction. So this is graph C. Now, by process of elimination, this equation is going to be for graph B. But what I want to point out is that this graph depends on both x and y. So if x and y are both positive, then the slope should be positive. Well, x and y are greater than 0 in quadrant 1. So if we look at quadrant 1 here, all the slopes are positive. We're good there. Okay. If x and y are both negative, okay, then the slope should be negative. X and y are both negative in quadrant 3. And if we look in quadrant 3, all the slopes are negative. Now in quadrant 2 and 4, it depends what the values of x and y are as to whether it's positive or negative. But one other thing that's sometimes helpful is setting it equal to 0. If the derivative is 0, that means the slope is going to be 0. If we solve this, you could have y equals negative x. If you solve that for when it's set equal to 0. So anytime the y coordinate is equal to the opposite of the x coordinate, which would be along this line right here, any of those points, the slope should be 0. And it is. So we have just verified in a couple of ways that graph B corresponds to equation 1. Okay, so a solution curve of a differential equation is a curve in the xy plane whose tangent at each point xy has a slope equal to the derivative. So what we want to do is sketch a slope field here at the indicated points for the differential equation y prime equals 2xy. And then use the slope field rather, to sketch the solution that passes through the point 1, comma 1. So there's quite a few points here. There's 20 points. Typically, you're not going to be asked to construct a slope field for 20 points. I'll get you started, and then we'll fill the whole thing in, and then do the second part of sketching a solution curve. So we could do that table of values again, x, y, and then y prime. So if we start, we could go in any kind of order you want. I'm just going to go in the upper left. So negative 2, comma 2. Okay. Well, actually, let's just put negative 2 here and 2 here. So y prime is 2 times the x value plus the y value, which is negative 2. So this slope right here would be a slope of negative 2. If I go 1 point down, that would be the point negative 2, 1. So 2 times the x value plus the y value, which is negative 3. So that's going to be even steeper. The next point down is negative 2, 0. So it's 2 times negative 2 plus 0, which is negative 4. So that's even steeper. And then negative 2, negative 1 would be the last point there. So it'd be 2 times negative 2 plus negative 1, which is negative 5. So you'd be even steeper at that point. So I'm going to go ahead and fill this in and show you what the whole thing is going to look like. So we have the whole graph filled in here, and so that would be our slope field. Now we're going to sketch the solution that would go through the point 1, 1. So what we do is we start at that point and we start to sketch the graph by making sure that our curve passes kind of parallel between all the tick marks around it. So if we start at that point, notice that the tick mark's pretty steep, so it's pointing in upward to the right, and we just would want to make our graph go kind of up like that. Now, as we move to the left, notice the slope tick marks level off, and then they become negative from there. So if we kind of go parallel, we're going to bottom out and then start to increase like that, kind of in a negative direction. So there we have it. There's our solution curve. It's not an exact science, but you're getting an idea of what it looks like in that situation right there. All right, guys. Well, that's it for this section, guys. Hope that was helpful to you. Reach out if you have any questions, and take care.